In the previous tutorial, we represented a vertex's rotated position values with vectors, and then used right-angled triangle trigonometry to calculate those values. You might have noticed that the z-axis that I'm referring to, which is the forwards direction, also known as the inter-screen axis, is actually labelled as the y-axis in Blender, which is because I'm basing the rotations on OpenGL's object space coordinate system. One thing I didn't illustrate in the previous tutorial is that the rotated vectors represent all points in 2D space, such that each point has its own x value and y value along those vector axes. For example, here's the orange coloured vertex example from the previous tutorial, in which we used vector representations to effectively rotate the axes 47 degrees, from here to here. And here's a new example which shows how this green coloured vertex, starting from a different position, becomes represented by those same vector axes after being rotated by the same angle. These rotated vectors can be referred to as the basis vectors, each which is equal in length to the x or y value of the vertex's initial position. The four vector representations at the bottom show before and after views of the rotation. I've simply aligned the y-axis for these two representations to provide an alternative way of looking at them. Much more fun is to watch these vector animations, carefully observe the yellow and red vectors, and you'll notice how their directions don't change, apart from being scaled to make them point in the exact opposite direction. Although these basis vectors are not perpendicular, and therefore never produce right-angled triangles as required for rotating points in space, the characteristic of being able to span all of 2D space remains exactly the same. The illustration shown on the right shows how any two basis vectors can effectively sweep through space. By scaling either one, the yellow vector in this case, the green vector then points to points in space that reside along a straight line. So now let's consider what it means to rotate around the x-axis, in contrast to how we've formulated rotating around the z-axis. Keep in mind that the coordinate system we're using is positive x pointing to the right, positive y pointing upwards, and positive z coming out of the screen pointing towards us. This means that Blender's x-axis points in the same direction, its y-axis points in the same direction but is labelled z, and its z-axis is both pointing in the opposite direction and labelled y. After rotation, this is the new z-axis and this is the new y-axis. When we rotate the viewport in Blender, we can see how the x-axis is pointing out of the screen towards us, in contrast to the z-axis pointing to the left being positive. Because the z-axis points to the left as being positive, compared to the default whereby x points to the left being negative, it means that this term needs to be made positive to get the correct z value, and this term needs to be negated to get the correct y value. We can also slightly modify the test program from the previous tutorial to enable us to check the results in the console window. In the next tutorial, we'll be taking a quick look at how to formulate the y-axis in the same manner, but also examining what happens when the angle of rotation is reversed. Please don't forget to subscribe if you'd like to see more. See you later.